I'm not buff, but I am quite familiar with this work. So I'll be sharing our latest results trying to do acoustic radiation force impulse imaging not only in diastole, which we've seen some really impressive results, particularly already in this session, but actually trying to do this all the way through systole, which gets a lot trickier. So pretty quickly, I think this is all pretty well understood by now that we're looking for new metrics of cardiac function. Stiffness is an important marker in addition to the kind of motion-based metrics that we've been seeing. And what we're going to look at here is actually really more like contractility, so the sort of relative stiffness between systole and diastole. We've had a lot of good work that goes through the cardiac cycle, but so far it's really only been successful in open chest and intracardiac preparations for the challenges of imaging transthoracically. So the hypothesis that we're testing is that within FDA limits, we can induce measurable displacements through the entire cardiac cycle transthoracically, and that those measurements will be robust, repeatable, and that they will indicate something about the cardiac stiffness. And ultimately, we want to develop metrics of function that we can start relating to disease states. So the methods, this is pretty standard. We're using a phased array imaging, I think parasternal, long and short axis. Some things to note: F number is decently high. The MIs and ISPTA are both within FDA limits. We get 20 ensembles per second, mainly a limit of how much data we can acquire at one time, and we're doing pulse inversion harmonic tracking. Okay, so a little diagram of how the acquisition looks is we're recording 10 milliseconds before and after the push, and the reason why we have such a long sort of reference time before the push is that particularly during systole, there's a lot of motion, and you have to remove this motion with some sort of filtering technique, polynomial frequency domain filters. And if you have your excited response during the time in which you're filtering, you have a difficult time knowing that what you have done is isolate the induced displacement from the sort of intrinsic displacement of the heart, which we know is quite large. So we actually recorded an equal amount of time before and after the push, and then we'll be saying that, okay, well, if we can suppress the 10 milliseconds of motion before the push effectively, there's a decent chance that those same filters will be helping to isolate the induced displacements. And so yeah, we record those 20 times per second. On the bottom left is the ECG acquired simultaneously with the little X's marking each acquisition. And then what you can do is you can pick out from the ECG points in systole and diastole and compare. This is the displacement traces. And so what we see is that during systole, we induce a smaller displacement than we induce in diastole. And you can look at the ratio of those peak values or the ratio of values at any fixed time after the excitation and call that some measure of contractility. So there's an example Bmode, which we take for reference to see what we're looking at. You can see we're focused on the septum in the middle. You can see the motion is actually pretty complicated as it beats and it moves left to right, but that's sort of the view you get. You have to live with the motion. We record very high frame rate tracking motion right down in a very narrow field of view in the middle. So we have a whole bunch of, I think it's probably 40 of these ensembles, which make an M mode aligned to the ECG, covering, I think, between 1 and 2 cardiac cycles. And if we calculate the displacements for each of those ensembles, then what we can play is an RFI movie, which if you've seen other talks on RFI image, it looks pretty similar to what we see. The only difference is that instead of a 2D RFI movie where we sequentially excite different regions of space and build that into our movie. In this case, we're just repeatedly exciting the same spot, and so we build an M-mode RP movie. And so what you're going to look at is that peak displacement. And what you can see is really nice alignment of the cardiac cycle to the trends that you see in the displacements. After the push, you get these big yellow blocks here, and if you trace those down onto your ECG, you see that those correspond to diastole, where we expect the tissue to be more compliant. As a reference to see how well we're doing at separating this motion from the cardiac motion, which is also quite large, we plot the displacements from before the push, and we see that, okay, yeah, here, they're all below a micron. So in this case, certainly, we're doing a decent job of projecting the intrinsic motion. To get these more quantitative metrics, we take each one of these M modes, we window out regions to mark systole and diastole based on the ECG, and then we can actually look at the histograms of what those displacements are through both space and some short time window. So on the top this is pre-push, so this is not the excitation. This is sort of what passes all the way through our motion filters, and it is nicely, centered about 0. That's good. We didn't induce any displacement. We don't really have much of a bias. You see higher standard deviation in systole. There's more motion, more of it leaks through. Whereas when we look at our actual measurements, the post-push displacements, we see a nice separation of these two distributions of displacements. And in this case, the diastolic-to-systolic ratio was 2.4. So yeah, 2.4 times as much displacement in diastole. So as has been mentioned a number of times, imaging transthoracically is really hard. I mean, this study was designed to also look at shear waves through the cardiac cycle, and it was nearly impossible. Only in a few diastolic cases where you have those same views actually in quite good agreement with what we've already seen previously. So yeah, you're pretty deep and you have a pretty small aperture, so lambda z over d kills you. You have acoustic clutter, but pulse inversion harmonic imaging has really done wonders to reduce that at a sort of manageable reduction in frame rate or temporal resolution. And cardiac motion is especially tricky in systole because the motion gets complex. And so we're going to look at some motion filtering techniques. There's an unlimited amount of optimization that you can do here. And there is, of course, fiber anisotropy, as we've seen, and we'll see those effects shortly. Okay, so to motion filter these, you get these raw displacements, and yeah, we're not inducing 75 microns of displacement. This is the background displacement. What we're inducing is this little bump in here. But if you filter it, I'm not sure if this is polynomial or frequency domain, but we get a nice removal of that baseline motion, and we can see pretty clearly the sort of 6 micron displacement, 5 to 6 microns. In systole, the motion's more complicated. It's not nearly as linear. It moves more, and as a result, you get bigger residuals. So in this case, it's harder to say, well, this is a 3 micron displacement because you have almost the same amount of jitter looking backwards in time. So one thing that we've done is we've tried in frequency domain filters to put different cutoffs. So I think there's a 1,000 hertz high cutoff, and this is a 25, 75, and 125 hertz low cutoff, looking just at the pre-push. So this is seeing how much leaks through, and as we bring that low cutoff of our band pass up, we see that there is a lot of low frequency, relatively low frequency motion intrinsic to the heart, and we tighten up our sort of residuals and bring them closer to 0. Of course, the side effect is that you're going to bias your estimates because they do have some frequency content in this range. So there's certainly more work to be done on characterizing this exactly. You can see the effect of the bias, but if you're going to try to make these metrics, this is just a much cleaner signal once you've filtered out some of that that low frequency noise. These two histograms have much better separation, and if it means that your clinical metric is based on a band-limited displacement, that could still be of clinical use. We compared the 3 different filters as well as 3 different polynomial filters, which we won't discuss for brevity, and did in fact see a bias that as you turned up you got more complicated filters that let you that remove more of the information. You had bias in your displacements in I think systole and diastole. There are 4 different patients. So here for one of the patients, we're looking at all the different measurements of displacement through the entire cardiac cycle from, I want to say, 4 or 5 different acquisitions that have all been now overlaid. So each acquisition covered, I think, 2 beats, which is why you have a few more points in the middle. But we get pretty nice repeatability, but with a pretty significant spread, right? And this is not, they're temporally aligned. You can actually, we didn't draw the lines, but you can kind of follow the lines that were recorded from individual acquisitions. And so you just get variation from beat to beat, and whether this has to do with respiration motion or I would say it's probably motion related, but the little white lines are the pre-push motion, so we're doing a good job of separating them, and there just is this level of variability. If we highlight out the different areas of systole and diastole, we can make these little plots showing, okay, so we have a low, good suppression of our pre-push jitter, and we have very nice separation of the diastolic and systolic, both with a high-pass filter and a second-order polynomial. We can look at that across all 4 patients. This is parasternal long-axis view, and you get significant separation in all of them, but at pretty dramatically different ratios. And with an N of 4, it's hard to say what that is. Larger studies will hopefully start to show this, but the error bars are small, the measurements are repeatable, and if you record enough heartbeats, you get a pretty good sense of what that kind of spatiotemporal distribution looks like. When we switch to the parasternal short axis view, I got one more slide, we see that the ratios change. Why they change differently in some patients than another is interesting and worth looking into, but we don't know yet. And we get ratios for all of them between 1.3 and 2.3. So it works, right? We can measure these displacements all the way through the cardiac cycle, and this opens up a whole new set of questions that we can look at. It also really enables doing kind of clinical studies because we could do it transthoracically. And yeah, of course, as everyone mentions, we got to get the SNR better. That always helps. But if we have time for questions, I'd be happy to try to answer them. Thanks.